Hello everyone, so today I'm going to be going over Chapter 1 of College Physics, which is Kinematics and Motion. So to start off, we must understand what kinematics are, and they are the mechanisms that explain motion. And I'll be getting into more detail in just a moment, but we must also understand that kinematics run in two directions. So the first direction is along the x-axis, so from west to east, east to west, or left to right, right to left. And a common example that you'll find in many problems is a car, because that is the most common daily example that runs along the x-axis, because your car does not go up and down. It simply goes left to right or right to left. And then the second direction that kinematics runs in is the y-axis, along the y-axis, so from north to south or south to north. And a common example of this is bouncing a ball up and down. So this basketball is going from north to south, south to north, or both if it's bouncing up and down. So next we must understand a few key terms that help us define kinematics in order to understand the equations and to solve for problems. So the first one is distance, which is abbreviated d, and it is also in meters, which is our basic unit in physics for distance. And our second term is displacement, which is abbreviated x. It is also in meters, so notice how they're both very similar. So the difference between the two, just some common differences, is that distance cannot be negative. So you cannot say that you traveled a negative distance. However, displacement could be positive or negative because displacement tells you direction. So I'll be going into further detail in a second, but we must understand the equation for displacement, which is change of x is x2 minus x1. So that's basically final displacement minus initial displacement. So in order to help distinguish the difference between displacement and distance, I'm going to be going over a quick example because they're both very similar and easy to get confused. So let's say our character Bob is trying to go from an initial position of 0 along the x-axis to the 15 mark, so 15 meters away, and then back to 5 meters away from his initial position. So the path would look something like this. And then same thing here, Bob does the same thing. So now, the way we're going to distinguish the difference between displacement and distance is by using the equation. So distance would be the total meters that Bob traveled. So Bob went to the 15 mark, so it'd just be simply 15 meters plus 5 meters. So he would have traveled 20 meters total. So that's the distance. Now, the difference is that his displacement would not be 20. It'd rather be, so you're going with the equation, change of x is equal to x final minus x initial. So Bob started off at an initial displacement of 0, so that would be the initial. And then his final displacement was 5. So Bob's displacement is simply 5 meters. So you can see the difference now between displacement and distance. Now a way to remember this is that, let me move the camera a little bit, distance explains the total meters traveled, essentially. So you're going from 0 to 15 and back to 5, so you traveled a total of 20 meters since your starting position. Displacement is simply how far you are from the initial position. So you are 5 meters away from your initial position because you disregard the middle path you took, and you're simply looking at the end result. So something very important to keep in mind about displacement and distance is that distance can never be negative, but displacement can be negative. This is simply because distance does not show direction, but displacement does. So if your displacement is negative, then it is simply saying that you went backwards or in the opposite direction of the axis, but you can never say that you traveled a negative distance. So next we must know that we also have time, and that will be a common, very common unit that's used in our equations. And time is always expressed as t, and it is always in seconds, so it can never be in hours or days. If it is, you must convert it back to seconds in order for the equations to work. And time can also never be negative because you can never have negative time. Next, for our kinematic equations, we have something called velocity, which is something you've probably heard of. This is also referred to as speed in many word problems. And the units for velocity are meters per second. So a common example of velocity would be on your speedometer. That tells you the velocity you're traveling, and it is also known as the speed you're traveling. So the equation for velocity is displacement over time. So as we just mentioned, we have displacement in meters and time in seconds, so your velocity is always going to be in meters per second. Next, we have acceleration, which is commonly confused with velocity, but they're very different. This one is in meters per second squared. So if we flip it over and look at the equation for acceleration is change of velocity over time. So since velocity is in meters per seconds already, let me go ahead and write that down. Meters over seconds. And then time is in seconds. When you divide the two, it makes the unit meters per second squared. So make sure to always check your units for acceleration because it could easily be confused with velocity. Now, in order to distinguish between velocity and acceleration, I'm going to be going over a few quick points so you remember what the differences are. So, to start off, velocity, as I mentioned before, would be a speedometer. That would be the common example of something that shows velocity. While acceleration, a common example would be a police car. So a police car starts off slow, and then when they see someone speeding, in order to chase after them, they must speed up. So that would be considered acceleration. Or acceleration can also be slowing down, so if you're coming to a red light, you would have a negative acceleration because you're slowing down. Now in terms of units, once again, velocity is always in meters per second, while acceleration is in meters per second squared. Acceleration can be either positive or negative. Velocity has to always be positive. So next I'm going to be going over a quick example in order to practice finding velocity. So the example is you drive past your block at a constant speed, and your block is 150 meters long, and it takes you 1 minute to cross your block. Find your velocity. So let's start off by drawing this example. So you're starting off at point A, and you're going to point B. You're going in 1 minute, so that would be t, your time. And your displacement in this case would be 150 meters. So now we're just going to bring back our velocity equation, which is displacement over time. So in this case, once again, displacement is 150 meters over time, but time is given in minutes in this problem, so we must convert it back to seconds. So it'd be 60 seconds. So in this case, after solving it, you'd get that velocity is 2.5 meters per second. And it's important that we always include meters per second, just so we don't get velocity and acceleration confused. So next, let's practice finding acceleration. So we have this problem. Now say you see a traffic light ahead on red, and you suddenly brake. So here's a little diagram to show the example. So you're going fast, and then you suddenly stop. You brake. And you brake in 4 seconds. Find your acceleration. So in order to solve this, we need our velocity from the last problem, which was 2.5 meters per second. And let's bring back the acceleration equation, which is a is equal to change in v over change in t. So in order to find acceleration, we must do 2.5 meters per second over change in time. So it's already in seconds. So now we just simply put it on the bottom. And now we calculate it. So 2.5 over 4 seconds is 0.625 meters per second square. So next I'm going to be introducing our 4 kinematic equations. These will be used to solve almost any physics problem. So we have these 4. They include velocity, acceleration, time, and displacement. So as I said before, just to recap, we're going to need to remember that t is always time, and that velocity is always v, acceleration is always a, and displacement is always denoted as x. Now the importance of these kinematic equations are that we are able to find missing factors that are not given in the problem. So like, let's say for example, you need to find final velocity, but you are given initial velocity, acceleration, and time, then you can easily find final velocity with this equation right here. And you could also rearrange this equation to find time if you're given all the other factors. And that's how all the equations work, so they're very important to understand in order to understand physics. So to start off, let's practice a quick acceleration problem using the kinematic equations. So a car is traveling at 17.7 meters per second. After 12 seconds, its velocity is 14.1 meters per second, so it is slowing down. Find the acceleration. So in this case, we know that the acceleration will be negative because it is slowing down. So acceleration will always be negative if an object is slowing down, and will always be positive if something is speeding up. So for this problem, we can simply use the equation v is equal to v initial plus acceleration times time. So let me write it out. Also note that this little 0 right here stands for node, and that will always mean that this is the initial of something. So if this is in front of something, that basically means initial. So we have the initial velocity, which is 17.7 meters per second. We have the time, which is 12 seconds. And we have the final velocity, which is 14 meters per second. So final velocity will always be just v, or it could be also vf, if you want to remember it. So next, we're going to find acceleration. So we have to rearrange this equation. So acceleration would be negative v initial plus v final over time. So next we just plug in these numbers. Now, after solving for acceleration, you'll find that a is equal to, negative, we can't forget the negative 0.3 meters per second square. And once again, this negative indicates that the car in this problem is slowing down from 17 meters per second to about 14. So the previous problem was an example of solving for acceleration along the x-axis using the kinematic equations, and this is because the car was going from a fast speed to a slower speed as it slowed down. And next we're going to want to understand what acceleration is along the y-axis. But in order to understand this, we must introduce a new unit. So this is gravity's constant, 9.8 meters per second squared, and this will always be used in place of acceleration for kinematic equations when you're going along the y-axis. So this could be throwing a ball up and down, launching a rocket, whatever it may be, we're always using this constant. So keep that in mind. So now let's say this water rocket is launched into the air. So we can say that the initial velocity is 0 because it starts off on the ground, not moving. And let's say the rocket's launched in the air for 5 seconds total before it comes down. So the total amount it takes for it to go up and down is 5 seconds. And we don't have final velocity. So this is what we're solving for. So at first it may not seem like we have everything needed to complete the equation, because we're going to be using this equation once again. So let me just write it out really quickly. But we must always remember that we do have acceleration. It is just the gravity constant, so the 9.8 constant. So that is our acceleration, meters per second, and this is squared. Okay, so now all we have to do is simply plug these in to find what the final velocity of the rocket is while it's in the air. So we're just going to plug in v is equal to 0 plus 9.8 times 5. So this would be the velocity of the rocket as it is 5 seconds into the air. So this is actually before it lands. So if the rocket is in the air for 5 seconds, the velocity would be 49 meters per second. So we just need to remember that whenever we're solving a problem that goes along the y-axis, we're using gravity's constant of 9.8 meters per second, unless it asks for acceleration, and it gives you all the other factors. But that's basically all. Those are the basics for kinematic equations. These are the equations once again, if you want to take another look at them. But these are simply what you need to know in order to start solving for the basic problems in chapter 1 of physics.